Let's start with this topic, Poynting Theorem, complete ground-up lesson. So part 1, what is this topic even about? Imagine sunlight traveling from the sun to your skin. It crosses empty space and when it hits you, it makes you warm. Something is carrying energy across that space, and that something is electric and magnetic fields of light wave. So Poynting theorem is simply the law of energy conservation written for electric and magnetic fields. It tells us three things at once. So how much energy is stored inside a field at that point, how much of that energy turns into heat or motion when it pushes on charges, and how much energy is flowing from one place to another, like water flowing through a pipe. How much energy is stored inside a field at any point, and how much is flowing from one place to another. These two sound similar anyway, so that's the entire goal. Now let's build up to the maths piece by piece. The force of a field, part 2, the force a field puts on a charge. So there is a rule in physics called Lorentz force law. It says if you have a charged particle Q sitting inside an electric field E and magnetic field B, this particle is moving with velocity V, and this particle is moving with velocity V, then the total force on it is said to be this QE plus QV cross B. So this is the electric force and the magnetic force. So don't worry about the cross symbol too much. It's called cross product, a way of multiplying two vectors that gives you a third vector perpendicular to both. The important thing to know about it, whatever direction you're moving in V, this velocity V, the force QV cross B always points sideways to your motion, because this is a cross product, and the result of cross product is always perpendicular to the two vectors, third vector perpendicular to both. So the product of this is going to be perpendicular to this, so the force always points sideways to your motion, never forward or backward along with it. So why does this matter in physics? Work done on an object only happens when a force pushes it along the direction it's moving, because work done is force times displacement. So if a force is not causing any displacement, I don't know, so but the direction would change, so displacement is happening, so I don't know. Anyway, so in physics, work done on an object only happens when a force pushes it along the direction it's moving. If a force pushes sideways, it doesn't speed the object up or slow it down, it just changes direction, like a string spinning a ball in a circle. The tension pulls sideways and the ball's speed never changes, so no work is said to be done on it. This is a weird definition, but okay. So the magnetic part of the force does zero work on the charge, because the magnetic force was perpendicular to the velocity, so it's doing zero work on the charge. Only the electric field part, QE, can actually give energy to the charge, speed it up, or take energy away, slow it down. This is the seed idea of the whole theorem. Only E can exchange energy with charges, B just redirects them. Part 3, power. How fast is energy being transferred? Power just means how fast work is being done. That is, in essence, P equals how fast the work is being done. So the rate of change of work per time. So work done per unit time, since force times velocity gives power, because work done is force times displacement, and displacement upon time is velocity. So now power is force times velocity. Force times velocity gives you power. This is basic mechanics. Fact, P equals F dot V. I don't know why the dot product, but anyway. So, and we just said that QE contributes work, and the power delivered to what? And we just said QE contributes work. So we are talking about work done, and only QE contributes work. So the power delivered to one single charge is, so we are only going to use electric force. Electric force was QE, so QE dot V is power now. Part 4, scaling up from one charge to a cloud of charges. In real life, we don't deal with one charge. We deal with wires, plasmas, and space full of countless charges. So the physicists use a quantity called charge density, written J. It's defined as J equals rho V, where rho is charge density, how much charge is packed into a unit volume. So how much charge is packed into a unit volume times the velocity, and v is just the average velocity of the charge cloud. Think of J as how much charge is flowing per unit area per second and in which direction. So how much charge is flowing for that particular volume is the current density. Yeah, current is moving charges. So okay, now imagine a tiny cube of space with volume dV. The amount of charge sitting inside that tiny cube is rho dV. Rho is charge density. So now charge density times that volume gives you the charges sitting inside that tiny cube. Using our power formula from part 3, the power delivered to just this tiny cube's charge is this. Rho is the formula, so rho dV. Now our rho is rho dV. This is velocity, this is volume, so rho dV times what? Wait. Now imagine a tiny this over here using our power formula from part 3. So this QE dot V. Using our power formula from part 3, the power delivered to just tiny cubes' charge is okay. So QE dot V we had. Now we are not talking about a single charge. We are talking about the charges inside that little volume. So that the charges inside that little volume is rho dV. So Q is replaced by rho dV. So now dP equals rho dV E dot V. This is the little power for that little volume. Divide both sides with dV to get power per unit volume. Why does that matter? I don't know. So power per unit volume, we divide this thing with dV and dV, so dV cancels out. Now rho E dot V becomes E dot rho V, and rho V was J, so E dot J. And we can do this because dot product is just multiplication of the magnitudes of those vectors times the cos theta, so this would not change the result, I guess. Anyway, so we just substituted rho v equals j from the definition above, so we have found something important. So E dot j equals power delivered by the field per unit volume to charges present in that volume. Okay, so if we now integrate this over some big region of space V, we get the total power delivered to all charges inside that region. So now we had this little dp. So anyway, so power delivered, if we integrate with respect to the volume, we have total power on one side, and integrating with respect to volume, we have this. This is the central quantity of the whole derivation. Right now it's written using E and J. Right now it's written using E and J, a field quantity and a matter quantity mixed together. Field and matter. This is current inside that volume and field. So okay, whatever. So our entire goal for the rest of this derivation is to rewrite E dot J using only the field quantities E and B, because that will reveal something purely about the field's own energy bookkeeping. So part 5, Maxwell's equation, the tools to eliminate J. So to turn J into something written purely into fields, we use two of the Maxwell's 4 equations, the two equation for the curl of E and curl of B. So now we can isolate J to get an expression, and we can substitute it back. As you can see, taking this to the other side, it becomes like negative of its whatever term. This term becomes negative, taking to the other side, and now divide both by mu naught, we get this equation. Now J is written entirely in terms of B and E, no mention of actual matter or charge anymore. That's exactly what we wanted. So a useful vector identity, just a tool to derive it. Before we substitute, we need one more piece of vector calculus grammar, standard identity, or that's always true for any two vectors field. So we are going to use this identity, standard vector calculus identity. I didn't know either, so this divergence of E cross B equals B dot curl of E minus E dot curl of B. Think of this as the same way you would think of a trigonometric identities like this. You don't rederive it every time you use it. You just know it's a mathematical, it's true mathematical fact and apply it. So rearrange to isolate the term we'll need. So we are going to be needing this part, I guess. Okay, so this part we would need. So taking it to the other side and bringing the other side to this side, we get this equation. Why is this useful? Because B dot this curl of E contains curl of E, and we already know it equals this curl of E equals this minus dB upon dt. So dB upon minus dB upon dt from Faraday's law, and the other piece E dot, sorry, del cross, I don't know, divergence of E cross B is going to become something very special very soon. So the Poynting vector itself, so this is going to be the Poynting vector anyway. So substituting J into E dot J, so now E dot this, we substituted the other thing we derived, whatever. So we substituted J in it in here, and taking the dot product, multiply the dot product across both terms inside the bracket. This is just distributing like this. So E dot this part becomes this. We had this in an identity, right? The vector identity anyways. So 1 upon mu naught is taken outside because that's just a constant. We're going to keep it a little separate, and E dot this part. Anyway, so now let's simplify the second term. We have E dot dE upon dt. So here's a small calculus trick. Another trick, by the way, if you take a vector and dot it with its own time derivative, you can rewrite it using the product rule. Recall the product rule from basic calculus. By the way, we have vectors in, and we are taking like dot product, but calculus is also involved. This is partial derivative. So anyway, so this is a calculus trick. Fine, so you can rewrite this using product rule. Recall the product rule from basic calculus. So this was the product rule, applying it for E dot E, which equals E squared. The square of the field says magnitude. The square of field says magnitude. What about cos theta? Is the cos theta 0 and cos 0 is equals 1, so maybe that is why E squared. Anyway, so this becomes this. The two terms on the right are identical. The two terms on the right are identical because dot product doesn't care about the order. Okay, so they doesn't care about the order, so these are same, so we can write it as this. So just added the same thing twice, giving factor of 2, whatever. So rearrange the small result. We wanted this part, right? This was identical to our equation what we had in here. So we're going to isolate this. As you can see, it becomes half of this E square upon d square upon dt. Substituting this back in our equation, we now have this. Okay, so we are now going to substitute for this part. Simplifying the leftover curl term, E dot curl of B sitting in the equation 1. So this is exactly what our vector identity from part 6 helps with. So we need E dot this curl of B equals this. Now we are going to use Faraday's law for this part to replace this. So B dot the right hand side of Faraday's law, whatever. So minus dB upon dt, it becomes minus of B dB upon dt. It's the same thing, right? So exact same product rule trick we used for part 7 this time with B instead. So this thing right here becomes this thing similarly. So we now have B dot curl of E equals minus half of dB square upon dt. Plugging this back in, we now have this in our equation. Combining 1 and 2. So combining 1 and 2, this is for E dot curl of v. So we are going to maybe substitute it back in place of this thing. So 1 upon mu naught, this part substituted. Distribute 1 upon mu naught across both terms inside the square bracket. So 1 upon mu naught and 1 upon mu naught. So okay, this is our new equation so far. So now just rearrange this, group the two d upon dt terms together. So this term and this term, maybe we are going to take out d upon dt. Yeah, since they are similar in form, so negative of d by dt, dono se common, we take it outside. So now we have epsilon naught half e square and half mu naught v square, half mu naught v square, whatever. And this part is untouched, is it? Negative of this del dot, I don't know, divergence, whatever. So 1 upon mu naught times E cross B. Naming the two important pieces. Now we have our equation and we're going to name the pieces. To naming the two important pieces, look at what's sitting in the two brackets. Physicists give both of them names because they represent physically meaningful things. Energy density called U. So this part is called U, this entire thing. Epsilon naught E square upon 2 and V square upon 2 mu naught. This is U. This tells you how much electromagnetic energy is packed into unit volume of space at any point. But how did they derive it? I don't know. So just like spring stores energy, or just like a spring stores energy when stretched, electric and magnetic fields store energy too. This formula is a known result from electrostatics. This formula is a known result. Okay, so from electrostatics and or magnetostatics, whatever. So similar to how you don't rederive F equals ma every time you use it. So we just recognize, and if we see ma, it is false, whatever. I'm saying whatever a lot. Anyways, so this is a known quantity. Energy density. This is energy density. The Poynting vector called S. So now other part. So the other part, this part, 1 upon mu naught E cross B. 1 upon mu naught E cross B equals S. This is the Poynting vector. This tells you how much electromagnetic energy is flowing through unit area. How much electromagnetic energy is flowing through unit area per second, and in which direction. Rewriting, so I don't know if this is also a known thing and we just identified it, or we actually, like, this became a thing after this Poynting theorem, whatever. So this tells you how much electromagnetic energy is flowing through a unit area per second and in which direction. Rewriting an equation with these names, so substituting u and s back, we get this equation. This is called the differential form of Poynting's theorem. It's true at every single point in space. Turning this into integral or region-wide form, the equation above is true at a point, but usually we want to know what's happening in a whole chunk of space, a volume V bounded by an outer surface S. Imagine a balloon. This is true at a point, but we want to, this equation above is true at a point, but usually we want to find what's happening in a whole chunk of space, a volume V bounded by an outer surface S. So imagine a balloon shaped boundary. To do that, integrate or add up both sides over the whole volume V. So integrating both sides with respect to volume V, this becomes E dot J dV by V. We talked about it, right? This was the power, I guess. Shall I check it? Yeah, this was the total power for that particular area. How much of that energy is being transferred to the charges or something. Fine, so the total power now, integrating the other side, we had minus du upon dt minus divergence of s minus du upon dt, integrating with respect to volume, integrating both terms. For the last term, we use a rule called divergence theorem. So we use divergence theorem for this part. A non-standard tool, we are not deriving it or just using it like a formula. So maybe this is the fourth thing that we are just using and we need to memorize for the exam. So this part can also be written like this. This rule basically converts how much field is spreading out from inside a volume into how much of the field is passing through the volume's outer boundary surface. How much field is spreading out from inside a volume and how much field is passing through the volume's outer boundary surface. So this is going to be equal, yes. Applying it, we substitute this for this to get this. Rearranging to put the surface term on its own side. So this to this side and this to this side, we get this thing. This is the integral form of Poynting theorem. So this right here is the integral form of Poynting's theorem. Usually the exact equation you're expected to derive in the exam. So the derivation is complete now. Part 12, what does each term actually mean? So they ask for the physical significance a lot in the question. So E dot J dV, this E dot J dV, this is the power, how fast the field is giving energy to charges inside volume V. Fast how fast the field is giving energy to the charges inside V, turning into heat or motion. So that's power, total power, I don't know. This d upon dt of u dv, how fast the stored field energy inside v is increasing. So the stored field energy inside v is increasing. How fast the stored field energy, I don't know. And this as dot dA becomes how fast energy is flowing out through the boundary of V. So the energy flowing out, the energy that's increasing inside that volume, stored, how fast the stored field energy is increasing. And energy is increasing, energy is flowing out, and how the field is giving energy. So the field is giving energy, that energy is increasing for that volume, and energy is also flowing out. So these are the three parts. So the energy that is going out equals the energy that it's getting and the energy that's increasing for that volume. So more the energy they are getting and the more the energy increasing for that volume, stored energy field inside V is increasing. Energy getting, energy stored equals energy leaving. What? I don't know. So anyway, so read as a sentence, flipping signs for intuition. Energy flowing in through the surface. Flowing in. This was going out, no? Maybe because of the negative signs, I guess. Yes, I was expecting them to add up because negative and negative makes up positive. So maybe if we take the negative outside and bring that to this side, so the energy going out, this was out, right, flowing out, becomes energy going in. So energy flowing in through the surface equal rate of energy getting rate of energy getting stored plus rate of energy being dissipated into charges. I don't know, it's still confusing. So this is just energy conservation, nothing new is created, energy is only ever stored, transferred or converted. Okay, so the Poynting vector has its own short answer topic. So a three marks question comes on just this Poynting vector. Sometimes the exams just ask define the Poynting vector. What does it represent? A separate 3-mark part, no derivation needed. So answer is pretty simple. So this was the Poynting vector. It represents the rate of flow of electromagnetic energy. This is electromagnetic energy, so it represents the rate of flow of electromagnetic energy per unit area measured in watts per meter square. Its direction is perpendicular to both EV. From the cross product is perpendicular to both EV for light wave. This is the same direction the wave itself travels. For a wave, its time averaged magnitude. For a wave, its time averaged magnitude is called intensity of the wave. Essentially, how bright or powerful it is. Rate of flow of electromagnetic energy per unit area. How much energy is flowing represents how bright or how powerful it is. If we take the time average magnitude, okay, so that becomes the intensity. Fine. Part 14, numerical worked in full. So typically a typical question, a plane radio wave has E equals this. So find B and intensity as average. The two formulas needed, known results not derived here. So E naught equals C V naught. The two formulas needed. So B naught can also be written as this, and SAV equals E naught, V naught upon 2 mu naught. So these are another things that we need to memorize. So a lot of memorizational stuff in this topic. Constants equals C equals the speed of light, and mu naught is 4 pi times 10 to the power minus 7 t dot m upon a, whatever this quantity is. I don't know what is this t. Is meter per ampere. What is this t? I don't know. So part 1, find B naught. So to find B naught, we just substitute and divide the numbers first. So 0.5 upon 3 becomes this. Then handle the powers. Minus 10 and plus 8 becomes minus 18. So B naught becomes this new number. Find SAV, E naught, we know, B naught, we know, and U naught, we know. So just substituting. Numerator first, we have this. Multiplying the plain numbers first. So 0.5 times this, we get this new number. Add the components because these are multiplying. So minus 29, we have this as our numerator, and denominator we have 2 mu naught. So 2 mu naught is this. Pi is value we are going to approximate. So now 2 times 4 time equals 8, and 8 times this, so 25.13 times 10 to the power minus 7. So minus 7 becomes plus 7. This becomes 21, yes, 22. So minus 22, and we divide these two numbers, plain numbers, we get this. This is going to take a lot of time if we don't have no calculator with us. So subtract the okay, so now we have SAV equals this. It was actually easy, but only if we knew like these two formulas. I don't know if the numbers for like pi and mu naught would be given or not. Anyway, so it's done. Summary what you now have fully exam ready. Full derivation of Poynting's theorem, differential and integral form done, meaning of every single term we saw, and standalone definition of Poynting's vector, and full worked numerical step by step. So the topic is complete.